The next topic is oblique trajectories, and this is the definition. Let fx comma y comma c equal to 0 be a one parameter family of curves. You already know that here c is the parameter. For different values of c, all of which are real numbers, you get different members of this family which are all curves. Now a curve that intersects all the curves of this family at a constant angle alpha which is not 90 degrees is called an oblique trajectory of this family. For orthogonal trajectory, the angle was 90, but for oblique trajectory it is some constant angle, but that's not 90. Now the next natural question of course is this: given this family of curves, how do we find an oblique trajectory which say intersects the curves of this family at this constant angle alpha? The first step, or should I say the first two steps, are exactly like what we did for finding orthogonal trajectories. You differentiate this equation on both sides implicitly with respect to x, obtaining another equation involving dy dx, and then in that equation you keep dy dx on one side and you push everything to the other side. That means you solve for dy dx. You get something on the right hand side which might have this arbitrary constant c. Then using that equation and this one, you eliminate c, and that will finally give you this differential equation. And from what we did for orthogonal trajectories, we already know what this equation means. It means that the slope of any curve in this family at a point x comma y is given by this right hand side. This means that if you choose some specific member of this family and say you choose a point on that member, at that point if you calculate this f of x comma y, then that will be the slope of that member at that point, or in other words the slope of the tangent to that member at that point. And so the angle of inclination of the tangent will be tan inverse of this slope, because if theta is the angle of inclination, then you know that slope equals tan theta. That's why. This just means that if we think of the tangent to an oblique trajectory of this type to that member at that point x comma y, then the tangent to this oblique trajectory will be having this angle of inclination, tan inverse of this, which is the inclination of the tangent to the original member, plus alpha. Let's see exactly why. This diagram makes it clear. Say this is your curve, which is any one member of this family corresponding to some specific value of c. And say your point x comma y is this point. At this point to this curve, this is the tangent, which has an angle of inclination. This is your horizontal line, or you can think of it as your x-axis. I mean, of course, it's not necessary that this is the x-axis. It may lie anywhere. It's just that this angle of inclination is the angle that this tangent makes with a horizontal line. In the positive direction. You already know these things. Now, this angle is this tan inverse of fx comma y. Okay. And this is an oblique trajectory to this curve, to this family actually, and wherever it intersects any member of this family, it makes an angle alpha with that member. So the angle between this oblique trajectory and the curve is alpha. Or in other words, that if you draw tangents to both the curves at that common point, then the angle between those tangents is this alpha. This is the tangent to the oblique trajectory at that point. Alright, then what is the angle of inclination of the tangent? This angle, which is this angle plus alpha. That's why. So if this is the angle of inclination of the oblique trajectory, then the slope of the oblique trajectory at that point will be the tangent of that angle, because that's how angle of inclination and slope are related. You know this fact from analytic geometry. So you now have tangent of this, which falls in the formula tan a plus b. You already know what that equals. tan A plus tan B divided by 1 minus tan A tan B. Because your first angle is already an arctangent value, that means tan inverse. So this is just f of x comma y. So that's how you get f of x comma y plus tan alpha divided by 1 minus f of x comma y tan alpha. So this is the slope of your oblique trajectory, or the same thing, the slope of the tangent to the oblique trajectory at that point. And slope is derivative. So now we can write the differential equation for the oblique trajectory. And that differential equation is this. Equating this slope with derivative, we get this differential equation. Solving this differential equation, we can find any oblique trajectory to a given family of curves, and that's what we are going to do now in an example. Example 3-4. Here we have to find a family of oblique trajectories that intersect the family of straight lines y equal to cx at angle 45 degrees. So you do understand that if we solve a differential equation like this, we don't get one solution, but rather we get a one parameter family of solutions. So each member of that family will be an oblique trajectory to the given family. I mean, in this case, which is this family of straight lines. And from the form of these straight lines, you can clearly see that they all pass through the origin. So it is that family of straight lines which we also considered before when finding orthogonal trajectories. Again, like last time, let's not write sentences, we just do the calculation. So this is our family of straight lines. What is the first step? We have to differentiate both sides with respect to x. Doing so, we get dy dx equal to c. So you see that the parameter of the family is still present. So you then eliminate this. In place of c, you write y divided by x. So that's how you have the differential equation of this family of straight lines devoid of the parameter c. I mean, you just consider this dy dx on one side and y over x on the other side. Now, the differential equation for any such oblique trajectory which makes an angle 45 degree with the members of this family will be given by this. And the differential equation is this. In this case, f of x comma y, that means our right hand side is y divided by x. So that comes here plus tangent of that common angle, which in this case is 45 degree. You can understand that this angle has been chosen to make things simple. But anyway, that's what it is. So this plus tan 45 divided by 1 minus y over x times tan 45. Tan 45 is 1. So we get y over x plus 1 divided by 1 minus y over x. And now we will simplify this a bit more. And simplifying this, we get this. You just multiply the numerator and denominator by x. So that way the numerator becomes x plus y, or y plus x, same thing, divided by x minus y. And from the look of this differential equation, you immediately see that it's a homogeneous equation. Actually, from here itself you see that it's homogeneous. So next you use this transformation, y equal to vx, where v is your new variable in place of y and x will remain, to turn this homogeneous equation into another equation which will be separable. And then you solve that equation. Find a one parameter family of solutions where there will be the variables v and x. You then eliminate v, you bring y back, and then that will give you a one parameter family of solutions, each member of which will be an oblique trajectory to our original family of straight lines. And if you go through that process, this is what you will ultimately get as your one parameter family of oblique trajectories. Ln of c square times x square plus y square minus 2 times tan inverse of y over x equal to 0. And you understand that here c is the parameter.